Hello everybody. Hope all of you all are safe and healthy. This is Divya from Department of Chemistry, ASC Independent PU College. In the previous video, we started with the discussion about the chapter General Principle and Process of Isolation of Elements. Let us continue with this chapter now. The last video, when we started about the discussion about the chapter, we got to know that for the extraction of metal, there are 4 steps involved. The 4 steps which are involved in the process of extraction of metal are crushing and grinding of the ore, concentration or pressing of the ore or benefaction of ore, isolation of metal from concentrated ore, purification or refining of metal. In simple, the 4 steps which are involved in this process of extraction is the metal which is in the form of ore is being first crushed and grinded. That is the first step. The second step, the earthy impurity, once you take out from the earth, the earthy impurities which are associated with this ore is being cleaned or removed. This is called as concentration of ore by different methods which I've already studied, that is leaching, froth flotation, hydraulic washing, magnetic separation, etc. And then next step is converting this concentrated ore into its oxide form by roasting and calcination, which I've already studied about this in the previous video. Once after converting into its oxide form, later it has to be reduced, that is metal oxides has to be reduced to metal because we require only metal. And the last step is purification or refining of metal. If you have not gone through the previous video properly, kindly go through it again before you continue. Now let us move on with the second step, that is after roasting and calcination, that is converting the concentrated ore into its oxide form. It has to be reduced to metal, that is metal oxide is being reduced to metal. We are going to study about this in this video. Okay, now in order to study about this reduction, we should know about the reactivity of the metals. Some metals are highly reactive, some metals are moderately reactive, and some metals are least reactive to atmospheric air and oxygen, etc. So when you look at these metals like alkaline earth metals, alkali metals, and aluminium, that is potassium, sodium, calcium, magnesium, and aluminium, these are highly reactive metals, are most reactive metals. And the metals like zinc, iron, lead, copper are moderately reactive, whereas mercury, silver, gold are least reactive metals. So different procedure is used to reduce this oxides of metal to metal. That is potassium, sodium, calcium, magnesium and aluminium being highly reactive are reduced by electrolytic method, whereas reduction of zinc, iron, lead, copper happens by using suitable reducing agent. And oxides of mercury, silver, gold is subjected to thermal reduction. So this is how the different methods are involved in reduction of this metal oxides to its metal, knowing their reactivity, that is most reactive, moderately reactive and least reactive metals. So when you look at this metal oxides of least reactive metals like gold, silver and mercury oxide, they can be easily reduced to get their metals just by thermal reduction. What is this thermal reduction? As it is, these metals, that is mercury, silver, gold, are least reactive to atmospheric air and oxygen. If at all, if some oxygen layer or oxide formation has happened, or the oxygen layer is present on the surface of the metal, they can be easily reduced to their respective metal just by thermal reduction, that is by heating alone. So when you take these oxides of these metal, what is your intention over here? You have to reduce your metal oxide to respective metals. So oxides of mercury, silver and gold can be easily reduced to their respective oxide just by heating alone. If you heat it for few minutes, the oxides of these respective metals are being reduced to metals. And this is called as thermal reduction. And next we have moderately reactive metals. Moderately reactive metals are zinc, iron, lead and copper. So these oxides of these metals are being reduced to respective metals by using suitable reducing agent. Now what is the suitable reducing agent, or which can be the suitable reducing agent? How to choose the suitable reducing agent? In order to know the better reducing agent for moderately reactive metal oxides, that is zinc oxide, iron oxide, lead oxide and copper oxide, this can be better studied or understood by thermodynamic principles of this metallurgy. The suitable reducing agent to reduce this metal oxides of moderately reacting metals can be studied by using or chosen by using thermodynamic principles. Thermodynamic principle helps in choosing the suitable reducing agent for your respective metal oxides. Thermodynamic consideration are very important in understanding metallurgical process. This helps in deciding the temperature and the choice of reducing agent in reduction process. The extraction of metal from their respective oxide by using particular reducing agent can be predicted by basic concept of thermodynamics. That is, based on your Gibbs free energy, entropy and enthalpy along with the temperature, we can predict the better reducing agent. It is given by the equation delta G is equal to delta H minus T delta S, where delta H is the enthalpy change, delta S is the entropy change for the process, T is the absolute temperature which is carried out, that is the process carried out. So again I'll repeat, delta G is equal to delta H minus T delta S, which you've already studied in the chapter of thermodynamics last year. That is, delta G is Gibbs free energy, delta H is change in enthalpy, delta S is change in entropy. For the reaction, that is Gibbs free energy or Gibbs energy change is also related to equilibrium constant. It can be related to equilibrium constant as delta G naught is equal to RT ln K. That is, delta G naught is what? Standard. Wherever you find this naught, it is what? Standard Gibbs free energy is equal to RT ln K. K is what? The equilibrium constant. R is universal gas constant. So you have another equation over here related to Gibbs energy, that is change in standard Gibbs energy, that is delta G naught is equal to RT ln K. We are aware that for a spontaneous process, always delta G must be negative. Remember this. For a spontaneous process, always delta G should be what? Negative. In the earlier classes of thermodynamics, we have already clearly studied, or we know that the feasibility or the possibility of the reaction, or only the reaction is possible only if delta G is negative. If delta G is negative, then the reaction is spontaneous and it will move in a forward direction. When this delta G value becomes negative, delta G becomes negative only when this change in entropy, that is delta S, becomes positive. Delta S is positive, and with increase in temperature, T delta S, the whole of this T delta S becomes more and more positive and delta G becomes negative. If delta G is positive, if delta S is positive, delta G is negative, the reaction favors the forward direction and it is a spontaneous reaction. Remember again, the criterion for the feasibility of the reaction or the possibility of the reaction is only when delta G is negative. Now, what if delta G is positive? If delta G is positive, then we call it as a non-spontaneous process. Now, how to make this non-spontaneous process a spontaneous process? This non-spontaneous reaction can be made spontaneous by coupling two different reactions or by combining two different reactions. The reaction one with positive delta G is combined with the other reaction having larger negative delta G value or greater negative delta G value. When you combine these two, the net delta G value, the overall delta G value will be negative. I repeat again, the reaction with the positive delta G value is combined with the reaction having greater negative delta G value. Then the overall or the net delta G value of both the reaction will be negative. So delta G becomes negative and the reaction is spontaneous. This is how the spontaneous and non-spontaneous reaction can be made spontaneous. Now, in order to choose a suitable reducing agent to reduce our metal oxide to metal, it is easier by using this Ellingham diagram, or it is studied or understood better by using this Ellingham's diagram. Ellingham diagram is a plot of standard free energy change, that is delta G naught against temperature for the formation of an oxide. The plot corresponds to the use of 1 mole of oxygen and 1 atmospheric pressure, that is 1 atm pressure. The important features of this Ellingham diagram is we don't get into this in detail of Ellingham diagram, and it is not that important in your syllabus. Just remember the use of Ellingham diagram in choosing the suitable reducing agent. The plots of metal oxides are straight line with a positive slope. These are a straight line with a positive slope, indicates that delta G naught increases with increase in temperature. That is, the value of delta G naught increases with increase in temperature. Some of the plots over here, you can see that there is a sudden change in the curve or sudden shift in the curve. The plot shows a sudden change or a sudden shift in the slope at certain temperature. It indicates that there is change in the phase. What do you mean by change in the phase? It changes to solid to liquid or liquid to gaseous state. That is called as what? Change in phase. So this indicates that the phase changes or there is change in the phase of gold, mercury. Delta G naught is positive because it doesn't require any reducing agent and it can be obtained very easily. That is, the metal oxides are easily reduced to get metal just by thermal reduction, that is just by heating at low temperature. So least reactive metal oxides are easily obtained just by heating it or by thermal reduction. In such cases, delta G naught becomes 0. And next is the plot of carbon dioxide. When you see, that is the formation of carbon dioxide from carbon. So formation of carbon dioxide using carbon is a straight line which is exactly parallel to that of the temperature. This clearly indicates that delta G naught does not vary with temperature in the formation of carbon dioxide. That is, the spontaneity of the reaction or formation of carbon dioxide does not depend on temperature. And next is the plot of carbon dioxide from formation of carbon monoxide is a negative slope, indicating that delta G naught value increases with increase in temperature. Now with this you can see that delta G naught value is what? In this curve you can see that delta G naught value increases with the increase in temperature, where this delta G naught becomes more and more negative. The plot of carbon monoxide is a negative slope. Any metal can reduce the oxides of other metal which lie above in the Ellingham diagram. This is most important when you look at this Ellingham diagram. Now what do you mean by this? It means that certain metals can easily reduce the metal oxides of the other metal. That is, example, aluminium, which is present over here, can easily reduce the oxides of iron oxide, chromium oxide and nickel oxide, which are usually present above in the Ellingham diagram. So it cannot reduce magnesium oxide, which is present. So from the Ellingham diagram, we can clearly know that the oxides of the metals which are present above in the Ellingham diagram can be easily reduced by using the metal which is present below in the Ellingham diagram, or in turn the metal which are present below in the Ellingham diagram can easily reduce the oxides of the metal which are present above in Ellingham diagram. I repeat again, that is, aluminium which is present below in the Ellingham diagram can easily reduce the metal oxides of iron, copper, chromium, etc. which are present above in the Ellingham diagram. Similarly, magnesium which is present below aluminium over here. So magnesium which is present below aluminium over here can easily reduce the oxide of aluminium. So this clearly indicates that the metals which are present below in the Ellingham diagram can easily reduce the metal oxides which are present above in the Ellingham diagram. The major use of this Ellingham diagram or Ellingham diagram is useful in selecting suitable reducing agent for given metal oxides. Of course, this Ellingham diagram also has certain limitations. That is, this Ellingham diagram is based on the assumption that reactant and products are at equilibrium, which is not actually true. That is, according to this Ellingham diagram, it considers that reactant and product to be in equilibrium, which is not actually true. And these conclusions are derived, or it is based only on thermodynamic concepts and not kinetics of the reaction. That is, it only helps us, or it gives the information about the possibility or feasibility of the reaction, and it does not speak about the kinetics, that is the speed of the reaction. So Ellingham diagram in turn helps only to choose the suitable reducing agent, and it does not speak anything related to kinetics of the reaction, that is how fast the reaction occurs or what is the time required for reaction to take place. So these are some of the limitations of the Ellingham's diagram. The major limitation is it does not speak about the kinetics of the reaction, that is the speed in which this reaction takes place, and this is based on the assumption considering that reactants and products are at equilibrium, which is not actually true. So this is all about Ellingham diagram, which helps us to choose a suitable reducing agent to reduce our metal oxides to metal. Now you can find the important features of Ellingham diagram and its limitation, which we just discussed. You can make a note of it for better understanding of the concept. Next is, the next example is reduction of, when you consider a reduction of cuprous oxide. Here you can see this is what the Ellingham diagram, that is the graph is plotted delta G naught versus temperature. Now you can see that the copper to cuprous oxide formation curve lies almost top, while that of carbon to carbon monoxide and carbon monoxide to carbon dioxide curve, they lie actually below this slope of cuprous oxide around the temperature range of 600 to 800 degrees Celsius. This means that it is very easy to reduce cuprous oxide to metallic copper just by heating with coke. The reason because I've already told in the previous slide, that is the curves which are present below the metallic curves which are present below can easily reduce the metal oxides which are present above. This, where choosing a suitable reducing agent is only better understood using this Ellingham diagram. So this clearly indicates, since the carbon monoxide or carbon's curves lies below this cuprous oxide formation, here you can see that the cuprous oxide formation with increase in temperature, this particular slope lies below, and hence coke acts as a better reducing agent for cuprous oxide, and by reduction of this we can obtain the metallic copper. And you can also make a note that the slope of carbon monoxide to carbon dioxide and carbon to carbon monoxide slope, the temperature below 1073 Kelvin. Please remember this, the temperature below 1073 Kelvin, the slope of carbon monoxide to carbon dioxide is lower, or it lies below. So the slope which lies below acts as a better reducing agent. You can see that the temperature below this range, that is 1073 Kelvin, or it is 800 degrees Celsius, carbon monoxide acts as a better reducing agent. Similarly, the temperature above 1073 Kelvin, coke acts as a better reducing agent, that is carbon to carbon monoxide. Here this carbon acts as a better reducing agent because this curve lies below. With increase in temperature or at high temperature, carbon or coke acts as better reducing agent. Kindly note the temperature, it is important and always asked. The temperature below 1073 Kelvin, which is the better reducing agent, it is carbon monoxide. The temperature above 1073 Kelvin, coke acts as a better reducing agent. Next is electrochemical principles of metallurgy. We've already studied about the reduction of oxides of least reactive metals like gold, silver, mercury, etc. by thermal reduction. And we have also studied about the reduction of metal oxides of moderately reactive metals, that is zinc, copper, etc. by choosing suitable reducing agent. That is what we studied till now, how to choose a proper reducing agent, or which is the best reducing agent using, it is chosen using what? Ellingham diagram. That is what we studied till now. Now what about this metal oxides of highly reactive metals? Metal oxides of highly reactive metals like sodium, potassium, magnesium and aluminium are reduced by electrochemical methods or by electrolytic reduction. In simple, by electrolysis. The process of extraction of metal by electrolysis from their fused salts is called electrometallurgy. Now what are we going to do here is that we are going to study about this electrochemical principle, how it is applied in reduction of highly reactive metal oxides. Okay, the reduction of this highly reactive metal oxides are either done by the process of electrolysis or by addition of more reactive metal as reducing agent. I repeat, it is reduced by the process of electrolysis or by adding highly reactive metal as a reducing agent. The thermochemical principle is based on the following equation, that is delta G naught is equal to minus NF E naught, where N is the number of electrons taking part in the redox reaction and F is the Faraday of electricity. E naught is the electrode potential of the redox reaction formed in the system. More reactive metals like alkali metal have greater negative electrode potential and it is difficult to reduce ions of such metals. In this case, we have to couple both the reactions, that is with least reactive metal, or you have to combine this with a least reactive metal. If the difference in the electrode potential of these two redox couple is positive, then delta G naught becomes negative and more reactive metal can displace the least reactive metal. In this case, you can see that iron is highly reactive than copper, so iron can easily displace copper from its salt solution. The least reactive metal will now, in simple, the least reactive metal will come out of the solution and highly reactive metal will get into the solution. That is, more active metal, iron, will go into the solution or it will get into the solution, whereas less reactive metal, that is copper, will come out of the solution very easily. The process of extraction of metal by electrolysis of their fused salt is called electrometallurgy. So next you can see that in this slide. In general, let me quickly summarize this. That is, highly reactive metals, potassium, sodium, calcium, magnesium and aluminium. Reduction of this is done by electrolysis or by adding a reducing agent of highly reactive metal. In simple, reduction of highly reactive metal oxides are done by electrolytic reduction, and moderately reactive metals like zinc, iron and lead is done by adding suitable reducing agent, which is chosen using Ellingham diagram, and least reactive metals like mercury, silver and gold are reduced by thermal reduction. The whole story of this principle, that is thermodynamic principle or electrochemical principle, helps us in reduction of the metal oxide to metal. I quickly repeat again the 4 steps which are involved in the process of extraction. The first step, we are going to crush and grind the ore. The second step, we are going to remove the earthy impurity which is associated with the ore. And the third step, we are going to convert this concentrated ore first to oxide form and then reduce from oxide form to its metal. So once the metal is in its oxide form, it is very easy to reduce that metal and to obtain a metal required. So that is what we have studied till now. So the second and the third step is completely done over here. That is, we have converted into its oxide form and we have also learned how to reduce this metal oxide to metal, how highly reactive metal oxides are reduced, how moderately reactive metal oxides are reduced, and least reactive metal oxides are reduced. In your syllabus, we have 4 important metal extraction to be studied in detail, that is extraction of aluminium, zinc, iron, copper. The reduction process is summarized over here, and we have studied about the first 3 steps till now. In the next video, we will also be studying about the purification or refining method and then study about this individual extraction of these methods in detail. We are going to study about the extraction of aluminium completely, zinc, iron and copper in detail by applying all these methods which you have studied now. Students, for better understanding of the concepts, I request you all to go through the video again and again. Anyway, this particular concepts of thermodynamic principle and electrochemical principle, you need to know how to choose the reducing agent, and it is not that important for your examination point of view. Thank you.